Are you able to see the screen now?
Yes, we can see.
Yeah. So this is the first class for tutorial class for superconductivity. So it's a 4-week course. So what we used to plan, like I think you attend other two TV's classes also now. So I normally going to do solve the problems related to this critical field and etc. Okay, superconducting material and critical temperature, critical field, Meissner's effect, those problems I'm going to solve today because these problems are based on the first week lecture. Okay,
Yes.
yeah, so yeah, okay, so let it be interactive session. You can ask something if you feel to, if you have some doubt or something, feel free to ask. I hope all you attended already the last week lectures to understand this. Okay. So we will solve the problem based on the mainly some formulas are there for critical field, critical temperature, and like, and by solving each question we can understand more about it. Okay. Okay, so we will go to the first problem. First problem is a superconducting tin has a critical temperature 3.7 Kelvin at zero magnetic field and critical field of 0.0306 Tesla at 0 Kelvin. Find the critical field at 2 Kelvin. So this is the question. So I am repeating questions once again. A superconducting tin has a critical temperature of 3.7 Kelvin at zero magnetic field and a critical field of 0.0306 Tesla at 0 Kelvin. Find the critical field at 2 Kelvin. So this is the problem. So let us first write what are the parameters given. So critical temperature it is given 3.7 Kelvin and its zero value field it is given 0.036 Tesla at T is equal to 0 Kelvin. Okay, now you have to calculate the critical field at temperature 2 Kelvin. Okay, so at T is equal to 2 Kelvin. So what you have to do, you have to solve it. So which formula you have to use this? You have to find the formula, write the formula for first h of t that is equal to h0 times 1 minus t divided by tc whole square. Now substitute the values which is already given in the problem. Although it's a direct. So it will be, you can submit 0.036 times 1 minus the temperature 2. T is 2 divided by 3.7 whole square. Now please calculate this and let me know what the answer you got. How much, what is the value of critical field. So the answer will be 0.0216 Tesla. Hope you all got the answer. So I'll explain the question once again. A superconducting tin has a critical temperature of 3.7 Kelvin at zero magnetic field and a critical field of 0.0306 Tesla at 0 Kelvin. Find the critical field at 2 Kelvin. So here the parameter which is given is already it is 3.10 DC value is given, critical temperature that is 3.7 Kelvin and critical field that is equal to 0.036 Tesla at T is equal to 0 Kelvin. You have to find the critical field at 2 Kelvin. Okay, so for that the formula is already there. Hc of T is equal to H0 times 1 minus T by Tc whole square. So substitute the values. It's a direct problem. You have to just substitute the values and you will get the answer. Critical temperature, critical field, it will be 0.0216 Tesla. I hope all of you following. So second question is the transition temperature of PP is 7.2 Kelvin. However, at 5 Kelvin, it loses the superconducting property if subjected to a magnetic field of 3.3 times 10 to the power 4 ampere per meter. Find the maximum value of H, which will allows metal to retain the superconductivity at 0 Kelvin. So here you have to find the value of H0 where the superconductivity will be there. Okay. So for that, as usual, first we will write the given parameter. So critical temperature is given 7.2 Kelvin. Okay. Now at 5 Kelvin it loses the superconducting property if subjected to a magnetic field. So the magnetic field Hc of T which is given. So it is 3 point. It is given. Okay. 3.3 times 10 to the power 4 ampere per meter at the temperature T is equal to 5 Kelvin. Okay. Now what you have to calculate? You have to calculate the H0 value which is in ampere per meter at T is equal to 0 Kelvin. Okay. So for this we can use the same formula. Hc of T is equal to H0 1 minus T divided by Tc whole square. Okay, now substitute the values here. So from there you have to calculate the H0 values because we should know what is the field, magnetic field here. So for that H0 is equal to Hc of T divided by this complete term. So it will be 1 minus T divided by Tc whole square. Okay, now you substitute all the values here. It will be 3.3 times 10 to the power 4 divided by 1 minus 5 divided by 7.2 whole square. So it will be 6.37 to the power 10 to the power 4 ampere per meter. Please try to solve it from your side. I'll explain this question once again. The question is the transition temperature of PP is 7.2 Kelvin, and however at 5 Kelvin it loses the superconductive property, is subjected to a magnetic field of 3.3 times 10 to the power 4 ampere per meter. Find the maximum value of H which it allow metal to retain the superconductivity at 0 Kelvin. So we have to find the magnetic field at the 0 Kelvin. Okay. So for that, which is already the parameter which is given, Tc is given and Hc of T is given at T is equal to 5 Kelvin. Now what we have to do at 0 Kelvin, what will be the H value? So for that we have to use the same formula, but here you have to find H0 value. So for H0 it will be Hc of T by divided by 1 minus T divided by Tc whole square. From there you have to substitute the value of Hc of T and T and Tc and find the answer for it. Okay, now we will go to the next problem. Okay. So the third problem is also similar to the earlier problem. So you please try to solve it first. The superconducting transition temperature of lead is 7.26 Kelvin and initial field at 0 Kelvin is 64 times 10 to the power 3 ampere per meter. Calculate the critical field at 5 Kelvin. So this is the question. So you have to find the superconducting transition temperature of lead. So It means the temperature is given, you have to, okay. So first you please try the answer, then I will solve it here. So here also the Tc value is given, so 7.26 Kelvin. Similarly, H0 value is given, that is 64 times 10 to the power 3 ampere per meter. Okay, and it is at 0 Kelvin. Now you have to find Hc of T at T is equal to 5 Kelvin. We have to use the same formula. Hc of T is equal to H0 times 1 minus T divided by Tc whole square. So now what you have to do? Substitute the values here. So it will be 64 times 10 to the power 3 times 1 minus T is given 5 divided by critical temperature T is 7.26 whole square, and find the answer for it. So here the problem is superconducting transition temperature of lead is 7.26 Kelvin. The initial field at 0 Kelvin is 64 times 10 to the power 3 ampere per meter. Calculate the critical field at 5 Kelvin. Okay. So in this situation, first we have to write the what are the parameters given. So critical temperature 7.26 Kelvin, which is given in the problem, and the critical value H0 is equal to 64 times 10 to the power 3. This is at 0 Kelvin. And now what is the you have to find? You have to find the critical field at the 5 Kelvin. So for that you have to use the formula Hc of T is equal to H0 times 1 minus T divided by Tc whole square. So substitute all the values. So then it will be 64 times 10 to the power 3 times 1 minus 5 divided by 7.26 whole square. So from this you will get the answer. After solving this mathematical part, you will get the answer 33.64 times 10 to the power 3 ampere per meter. Now if you go to the next problem, okay, the problem is critical field of niobium Nb is 10 to the power 5 ampere per meter at 8 Kelvin and 2 times 10 to the power 5 at 0 Kelvin. Calculate the critical temperature. So till now whatever the problems we are solved, it there you have to calculate the critical field. Now we are going to calculate the critical temperature. The formula is same, but how you are explaining, means understanding the formula, using the formula and solving the problem, that is more important. Okay. So in this cases, what are the parameters given? Hc of t, which is given 10 to the power 5 ampere per meter. Okay, the temperature is T is equal to 8 Kelvin. Now, H0 value is also given, that is equal to 2 times 10 to the power 5 ampere per meter at T is equal to 0 Kelvin. So, this many parameter is given. Now, what you have to find? Critical temperature Tc you have to calculate. So, for this, just we have to, first we will write the formula, basic formula. Hc of T is equal to H0 times 1 minus T divided by Tc whole square. Okay. Now from there you have to first extract the Tc value, then substitute the parameter numerical values for the problem. So here first we will write Hc of T divided by H0 is equal to 1 minus T by Tc whole square. Okay. Now T divided by Tc whole square will be 1 minus Hc of T divided by H0. Okay. Now from this T square is equal to, what you will get? 1 minus Hc of T divided by H0 times Tc square. Okay. Now we need the value of Tc. So Tc will be T divided by root of all these terms. So it will be 1 minus Hc of T divided by H0. So here you have to substitute all the values now. So after substituting all this value, what you will get? 8 divided by root of 1 minus 10 to the power 5 divided by 2 times 10 to the power 5. So please find the answer for solve this mathematical part and find the answer in Kelvin. So in this problem, the critical field is given and at the temperature, and that field at the temperature 0 Kelvin also given. You have to calculate the critical temperature of niobium. For that we have here we written the all the parameter which is given in the problem. Now we have to use our basic formula. It will be Hc of t is equal to H0 times 1 minus T divided by Tc whole square. Okay. From that Hc of t divided by H0 will be 1 minus T divided by Tc whole square. And from there you have to get the value of Tc, expression for Tc. For that T divided by Tc whole square will be 1 minus Hc of t divided by H0. From there you have to take the Tc square value, that will be 1 minus Hc of t divided by H0 Tc whole square. From there you will get the value of Tc, that is equal to T divided by root of 1 minus Hc of t divided by H0. Substitute the value. T corresponds to 8 and Hc of t will be 10 to the power 5 and H0 will be 2 times 10 to the power 5. Then you will get the answer will be 11.31 Kelvin. So this will be the critical temperature for niobium in this equation. Now let us move the next problem. Okay, the question is the critical temperature of a superconductor when no magnetic field applied, that is Tc. Okay, find the temperature at which the critical field become half of the value at the 0 Kelvin. So it is just like a, we have to find the temperature at which the critical field become half of its value at 0 Kelvin. Okay, so what are the things given? Hc of t is given, that is H0 divided by 2 at t. Okay, now Hc of t will be, we know the formula, H0 time 1 minus T divided by Tc whole square, right? So now here we can write it as 1 minus T divided by Tc whole square will be Hc of T divided by H0. Okay, so T divided by Tc whole square will be 1 minus Hc of T divided by H0. Okay, now from this T square will be what? 1 minus Hc of T divided by H0 times Tc square. Okay, so from there we will get the value T is equal to, it will be root of 1 minus Hc of T divided by H0 times Tc. Okay, now here we have to apply the condition. So here you will get root of 1 minus Hc of t will be H0 by 2. That is the condition given in the question. Okay, times Tc. So it will be how much? H0 will cancel and root of 1 over 2 times Tc. That will be root of 0.5 times Tc. You can write it as 0.707 Tc. please try to solve from your side. Then we'll go to the next problem. So here the problem is the critical temperature of a superconductor when no magnetic field is applied is Tc. Find the temperature at which the critical field become half of its value at 0 Kelvin. So the condition which is given is Hc of T is equal to H0 by 2 at T. Okay. Now we have to use our formula. It will be Hc of T is equal to H0 times 1 minus T divided by Tc whole square. Okay. Now 1 minus T divided by Tc whole square is equal to Hc of T divided by H0. Actually our aim is we have to get the T value and how it related to Tc, that we have to find it. So for that we have to extract the T from the formula separately. So we are doing those steps here. So 1 minus T divided by Tc whole square is equal to Hc of T divided by H0. And here you can see T divided by Tc whole square is equal to 1 minus Hc of T divided by H0. Now from the T square you can write it. It will be 1 minus Hc of T divided by H0 times Tc square. Then T will be root of this value times Tc. Now what you have to do? You have to submit the Hc of T value here. So H0 by 2. Then you will get the answer root half of Tc. It will be 0.707 Tc. Okay, now we will go to the sixth problem. This problem is little bit different from the earlier problems. Okay. Now here the calculate the critical current density for 1 millimeter diameter lead wire at 4.2 Kelvin and 7 Kelvin. Okay. A parabolic dependence of magnetic field strength Hc may be assumed for the calculation. And for a lead, Tc is 7.2 Kelvin and Hc will be 6.5 times 10 to the power 4 ampere per meter. Okay. Now here first we have to know one value, critical current IC, that you can write it as Hc times 2 pi r. Okay, you have to know this. And the current density Jc will be Ic divided by pi r square. It's current density, so current divided by the area part. Okay. Now the what are the parameters given in the problem? So parameter which are given in the problem, it is Hc of T is equal to 0 Kelvin, that is given 6.5 times 10 to the power 4 ampere per meter. Now you have to calculate Hc of T is equal to 4.2 Kelvin. Okay. Now we know the formula. Hc of T is equal to Hc of 0 times 1 minus T divided by Tc whole square. Okay, so we are going to calculate Hc of 4.2, that will be 6.5 times 10 to the power 4, 1 minus T will be 4.2 and Tc will be 7.2, its whole square. Okay, so then we have to calculate this, we have to find the answer for it. Next, what you have to find? The value of IC. So once you get HC value, then substitute 2 pi r radius is also given, diameter is given, you can calculate the radius and substitute the value, you will get the IC value. Similarly, you have to do for the TC is equal to, temperature is equal to 7 Kelvin also for the same thing. Okay. So here you will get the Hc of T value will be 4.28 times 10 to the power 4 ampere per meter. Okay, once you get the Hc of T, you can calculate Ic, that will be Hc times 2 pi r. So here r will be what? Diameter is 1 millimeter, so r will be 0.5 millimeter. So substitute all those values here. So 4.28 times 10 to the power 4 times 2 times 3.14 times 0.5 times 10 to the power minus 3. You will get the I value, that will be 134.39 ampere. Okay, this is correspond to the H temperature 4.2. Okay, now what you have to do? You have to similarly you have to use same thing here also. T is equal to 7 Kelvin. So same formula HC T is equal to 7 Kelvin. That will be HC of T is equal to 0 Kelvin times 1 minus T divided by Tc whole square. Okay, now substitute all the values here. So it will be 6.5 times 10 to the power 4 times 1 minus 7 divided by 7.2 whole square. So it will be 0.356 times 10 to the power 4 ampere per meter. Okay, once you got the H value, then substitute it's for IC. So it will be HC times 2 pi R. So you will get the answer 0.356 times 10 to the power 4 times 2 times 3.14 times R will be 0.5 times 10 to the power minus 3. You will get the answer 11.17 ampere. Okay, now you got the current. So both case you have to calculate the current density. So in this case current density JC will be IC divided by pi R square. So substitute all the values. So IC is given here and pi and R values you know. Finally you will get the answer 1.42 times 10 to the power 7 ampere. Okay, similarly in this case also what you will get, JC will be JC is equal to IC divided by pi R square. Substitute all the values here. The IC will be 134.39 and pi R already you know. So substitute all those values. You will get 1.71 times 10 to the power 8 ampere per meter square. So I'll explain this problem once again, then we will go to the next one. Okay. So calculate the critical current density. You have to calculate for 1 millimeter diameter lead with temperature is given 4.2 Kelvin and 7 Kelvin. A parabolic dependence, that you have to assume the calculation. And for a lead, Tc is equal to 7.2 Kelvin and Hc is given 6.5 times 10 to the power 4 ampere per meter. Okay. Now we have to know two formulas first. What is the current value and the relation between current and HC. So IC will be HC times 2 pi r and JC is equal to IC divided by pi r square. Okay. Now these are the parameter which is given in the problem. So you have to first calculate HC for 4.2 similar, and from there you have to get the IC value. From the IC you have to get the value of JC. Okay. Once you know the formula, you can easily solve it. So for this HC you have to calculate, it will be formula HC of 0 is equal to 1 minus T divided by TC whole square, and substitute the values which is given in the problem and you will get the HC value. It will be 4.28 times 10 to the power 4 ampere per meter. Okay, now do the IC value. So critical current will be HC times 2 pi r square. So it 2 pi r, so it will be 134.39 ampere. Now from those IC value you can calculate the critical charge current density. It will be JC is equal to IC divided by pi r square. So it will be 1.71 times 10 to the power 8 ampere per meter square. Okay, same procedure you have to do for the next part also. So for temperature T is equal to 7 Kelvin. So for that Hc of T is equal to 7 Kelvin is equal to Hc of T is equal to 0 Kelvin times 1 minus T divided by Tc whole square. Substitute all the values, you will get the Hc value. It will be 0.356 times 10 to the power 4 here. Then from there you have to calculate the IC value. IC value you will get 11.17 ampere. From there JC, the current density value will be 1.42 times 10 to the power 7 ampere per meter square. After this we will go to the next problem. So next problem is calculate the critical Okay, so the next problem is calculate the critical current which can flow through a long thin superconducting wire of aluminium of diameter 10 to the power minus 3 meter. The critical field of aluminium is 7.9 times 10 to the power 3 ampere per meter. So okay. So in this case, you have to calculate the critical current. So we already discussed earlier problems. If you see here, you can find the critical current formula. It will be Hc times 2 pi r. So here this problem, you have to just substitute the values. It's Hc is already given and diameter is given. From there you will get the R value. Then just substitute that in the formula. You will get the critical current for long wire of aluminium. Okay, so here you can get the formula IC is equal to 2 pi r HC. Okay, substitute here 2 pi times R will be 10 to the power minus 3 divided by 2. So it will be 10 to the power minus 3 divided by 2 times HC value 7.9 times 10 to the power 3. So you can cancel here these two. Then what will be remaining? 7.95. This will be the answer for this question. Now we will go to the next problem. A superconducting lead has a critical temperature of 0.726 Kelvin at zero magnetic field and critical field of 8 times 10 to the power 5 ampere per meter at 0 Kelvin. Okay. Now find the critical field at 5 Kelvin. So you have to calculate. So what are the parameters given here? The critical temperature of 7.26 Kelvin at zero magnetic field and critical field of at 0 Kelvin. Okay, now let us write first what are the parameters given. So Tc is given, that is 7.26 Kelvin. Okay, and Hc of 0, which is given 8 times 10 to the power 5 ampere per meter. Now you have to calculate Hc of T is equal to 5 Kelvin. Okay, this one you have to calculate. This is our general basic formula we have to use. Hc of T is equal to Hc of 0 times 1 minus T square divided by Tc square. Okay, just substitute all the values. So you will get 8 times 10 to the power 5 times 1 minus 5 square divided by 7.26 whole square. Substitute the value and you will get the answer also here. This was a direct problem. Here you will get the answer 4.2 times 10 to the power 5 ampere per meter. Okay, now we will go to the next problem. When first the problem is the critical temperature. It's temperature. Okay. Temperature for mercury with an isotropic mass of 199.5 is 4.185 Kelvin, and calculate the critical temperature of isotopic mass changes to 0.203.4. Okay, now here the isotope the mass is given and critical temperature is given. You have to calculate the critical temperature when mass at 203.4 units. Okay, now in this case what are the parameters given? Tc is given. Tc is 4.185 Kelvin. Okay, now m1 will be 197.5 units. Okay, now you have to calculate Tc2. Tc1 we can take it, Tc2 you have to calculate. Okay, and m2 is given, that is 203.4 units. Now we know that critical temperature will be proportional to minus m to the power minus 1 by 2. Okay, so we can write it at Tc, that is equal to a constant. Let us take the constant as lambda, then it will be half. Okay, now we can write two equations. Tc1 is equal to lambda, constant will be same, m1 minus half. Similarly, Tc2 is equal to lambda times m2 the power. So let us give the name for this equation 1 and equation 2. Now you do equation 1 divided by equation 2. You will get the value Tc1 divided by Tc2 is equal to m1 divided by m2 whole to the power minus 1 over 2. Okay, from this you can calculate Tc2 is equal to Tc1 times m2 divided by m1 to the power minus half. That you can write it as Tc1 times m1 divided by m2 whole to the power half. Okay, now substitute the values just here. So m1 m2 you have, and similarly Tc1 also you have. So just substitute those values and find the answer Tc2 in Kelvin. this problem, you will get the answer 4.14 Kelvin. Okay, so here what we have done, we have the relation here Tc proportional to the mass power minus half. Okay, so from this proportionality we did the we solved the problems. Okay, now next problem also we will like a similar kind of problem. It's related to penetration depth. Okay, so if you see the penetration depth of a lead are, it's in angstrom. Okay, 396 angstrom and 1730 angstrom at 3 Kelvin and 7.1 Kelvin respectively. Calculate the critical temperature. Okay, you have to calculate the critical temperature for this situation. So for here, first let us write what are the parameters given. So for the first parameter which is given lambda 1, that we can take it as 396 angstrom. So it will be 396 times 10 to the power minus 10 meter. Okay, now lambda 2 also given, that is 1730 angstrom. So it will be 1730 times 10 to the power minus 10 meter. Okay, now let's the temperature T1 is given 3 Kelvin and the temperature T2 is given 7.1 Kelvin. Okay, these are the parameters given. Now you have to know the formula. Lambda is equal to lambda 0 times 1 minus t to the power 4 divided by tc to the power 4 to the power minus half. Okay, now what we have to do, for each case we can write it. So in each case what will happen, lambda 1 we can take it as lambda 1 is equal to lambda 0 times 1 minus t1 to the power 4 tc to the power 4 whole power minus 1 over 2. This we can call it as equation 1. Similarly, lambda 2 also, lambda 0 times 1 minus t1 power the power 1 4 and tc power 4 whole to the power minus, it will be t2. Okay, it will be second equation. Now divided equation 1 by equation 2, you will get the value lambda 1 divided by lambda 2 is equal to lambda 0 will cancel in each case, so it will be 1 minus t1 to the power divided by 4 divided by tc power 4 times minus 1 over 2 divided by 1 minus t2 power 4 divided by tc power 4 whole to the power minus 1 by 2. Okay, now we have to solve and find the value of tc from this formula. So it is like a normal mathematical step. You have to solve it here. So what you will get, do the cross multiplication. So you will get lambda 1 times 1 minus t2 power 4 divided by tc power 4 whole to the power minus 1 by 2 is equal to lambda 2 times 1 minus t1 power 4 divided by tc power 4 times minus 1 over 2. Okay, now let us take the square on both sides to get tc properly outside. So take the square, then you will get lambda 1 times, and take the square and change it. Minus 1 will be, if you compare the another side, it will be plus 1. So then our form equation will be lambda 1 times 1 minus t1 power 4 divided by tc power 4 is equal lambda 1 square, it will come equal to lambda 2 square times 1 minus t2 power 4 divided by tc power 4. Okay, now what we can expand it. So lambda 1 square minus lambda 2 square is equal to what we will get, lambda 1 square t1 to the power 4 divided by tc power 4 minus lambda 2 square t2 power 4 divided by tc power 4. Okay, so here now we need tc power 4. So tc power 4 will be lambda 1 square t1 to the power 4 minus lambda 2 square T2 power 4 divided by lambda 1 square minus lambda 2 square. Okay. Now substitute all the values. Lambda 1 is given, T1 is given, T2 is given, lambda 2 is given. Substitute all the values, you will get the value for Tc power 4 and take the 1 by 4th of it. You will get the temperature, critical temperature. Okay. So what is the answer you got here? You have to substitute 396 square 3 to the power 4 minus 1730 square 10.1 to the power 4 divided by 396 10 power 4 square minus 1730 square. Then finally you will get the answer 7.193 Kelvin. So it is a little bit lengthy problem, like the just rearrangement of the formula. Then you can find the answer for it. Okay, now we will go to the next problem. So next problem is, for mercury of mass 202, value of isotopic constant alpha is 0.5 and the critical temperature is 4.2 Kelvin. Find the transition temperature for isotope of mercury of mass 200. Okay, so if you see here, two masses are given. One is M1, that we can take it as 202. Another one is M2, that you can take it as 200. Then critical temperature Tc is given 4.2 Kelvin and alpha value which is also given 0.5. Now you have to calculate, okay, Tc1 corresponding to 201, Tc2 you have to calculate. Okay, now we know that formula, Tc1 times m1 power alpha, which is equal to Tc2 m2 power alpha. Okay, from there you have to calculate Tc2, so it will be Tc1 m1 power alpha divided by m2 power alpha. So all the values are here. You have to just calculate it. So Tc1 you can write it as m1 divided by m2 whole power alpha. Then substitute the value Tc1 here. It will be 4.2 and m1 and m2 will be 202 divided by 200. Power alpha will be 0.5. So substitute all the values. You will get the temperature. Tc2 is equal to, will be in Kelvin. So how much you are getting Tc2 value? Tc2 will be 4.2209 Kelvin. Okay, so here only one thing you have to remember. You have to remember the formula. So almost every problem, if you see one first problem, few problems we solve related to HC values, like the one base formula HC is equal to H0 times T1 minus T by Tc whole square. Okay, that formula. And second one, what we did that different kind of problem means we have to we did with the penetration depth, and here we are using isotropic mass and how it is related to the critical temperature. So these three kind of problems only mainly will be for the first portion, first week class. You will get it. So if you see here, in this case the formula will be like Tc1 m1 alpha is equal to Tc2 m2 alpha. Here alpha is the isotropic constant, so that you have to remember what is alpha. Okay, then you can solve the problem very easily. Now let us move to the next problem. The critical temperature of neobium is 9.15 Kelvin at 0 K, and at the critical field is 0.195 Tesla, and calculate the critical field at 6 Kelvin. Okay, so in this situation T and Tc is given and HC value is also given. So this you have to use just normal our basic formula and try to solve it. So here the parameter which is given Tc which is given is equal to 9.15 Kelvin, and Hc of 0 which is given 0.196 Tesla, and T is given that is 6 Kelvin, and Hc you have to calculate. For this we have to use our basic formula that Hc of Tc is equal to H0 of T times 1 minus T divided by Tc whole square. Okay, now substitute all the values here. It will be 0.196 times 1 minus T will be 6K divided by 9.15 K whole square, and substitute all the values. You will get 0.196 times 1 minus 0.42999, that will be 0.1117 Tesla. So this will be the answer for this problem. It's just like a direct problem. You have to just substitute the values whichever is given. So now we will go to the 13th problem today's session. So this problem is the critical temperature of a metal with isotropic mass. So here the problem related to the isotropic mass. So we have to solve these problems related to only this formula. So if you see isotropic mass and constants and all, then just remember this formula. The critical temperature of metal with isotropic mass 199.5 is 4.185 Kelvin, and calculate the isotropic mass if the critical temperature falls to 4.133 Kelvin. Okay, so now let us first write what are the parameters given here. So here M1 is given, that is 199.5, and its corresponding TC1 which is given 4.185 Kelvin. Okay, now we have to calculate M2 and TC2 which is given 4.133 Kelvin. Okay, so in this case again we have to use the same formula. So it will be TC1 M1 alpha is equal to TC2 M2 alpha. Okay, now we need M2 alpha, that is equal to TC1 divided by TC2 times M1 alpha. Okay, but here what alpha is 0.5, then root of M2 is equal to TC1 divided by TC2 root of M1. Okay, now just substitute the values here. TC1 will be 4.185 divided by TC2 will be 4.133 times root of 199.5. From there you will get the value root M2 is equal to 14.381. From there you will get M2 is equal to 0204.55. So this is also just direct application of the formula. You have to find the isotropic mass M2 from the problem. Now we have to solve the next problem. Calculate the critical current through a long wire. So here you have to calculate the critical current through a long thin superconducting wire of radius 0.5 millimeter. Critical field is 7.2 kilo ampere per meter. Okay, so now just see what are the values are given. So Hc is given critical field, it is 7.2 kilo ampere per meter. So it will be 7.2 times 10 to the power 3 ampere per meter. Okay, now radius is given, r is equal to 0.5 millimeter. So it will be 0.5 times 10 to the power 3 meter. Now we need to find I critical current. So that's already we discussed some previous earlier slides. So it will be 2 pi r times hc. Just substitute the values here, you will get the answer. So 2 times 3.14 times radius will be 0.5 times 10 to the power minus 3, then times 7.2 times 10 to the power 3. So finally you will get the answer here. So the answer, please calculate all this and let's find the answer for IC. So we will solve one more problem today. So this problem is calculate the critical current for the superconducting wire lead having diameter 1 millimeter at 4.2 Kelvin. The critical temperature of lead is 7.12. HEC is given 6.5 times 10 to the power 4 ampere per meter. Okay, so what are the parameters given here? HC of 0, that is 6.5 times 10 to the power 4 ampere per meter. Okay, radius it will be 1 millimeter, diameter so 0.5 millimeter, that you can write 0.5 times 10 to the power minus 3 meter. Then T is given 4.2 Kelvin. Okay, now TC, which is also given 7.18 Kelvin, and you have to find IC value. Okay, so what we have to do here, we have to first apply the basic formula. HC is equal to HC of 0 times 1 minus T divided by TC whole square. Okay, from there substitute it 6.5 times 10 to the power 4 times 1 minus 4.2 divided by 7.18 whole square. Okay, so it will be 6.5 times 10 to the power 4 times 0.06573. Okay, so your final answer of HC will be 42.758 kilo ampere per meter. So this is just HC value. From this HC value you have to calculate IC. IC you know already, it will be 2 pi r HC. So substitute HC value and pi and r value, you will get the answer for IC. Here if you substitute the values, you will get 2 times 3.14 times radius 0.5 times 10 to the power minus 3 times 42.758 times 10 to the power 3. So substitute it is here, then you will get the answer 134.26 ampere. So this will be the answer for it. Okay, so we will solve one more problem very quickly and we will finish today's class. Okay, so the critical field of a vanadium is 10 to the power 5 ampere per meter at 8.58 Kelvin and 2.2 times 10 to the power 5 ampere per meter at 0 Kelvin. Find the transition temperatures. You have to find the transition temperature here. So what are the parameters given? Hc is given 10 to the power ampere per meter and Hc of 0 which is given 2 times 10 to the power 5 ampere per meter and T is equal to 8.58 Kelvin. Okay, so now we know that Hc is equal to Hc0 times 1 minus T divided by Tc whole square. From there, just do Hc divided by Hc0 is equal to 1 minus T divided by Tc whole square. From there, T divided by Tc whole square is equal to 1 minus Hc divided by Hc0. Okay. Now we need to calculate the Tc, critical temperature, that is transition temperature here. So for this we need to Tc will be, so now solve with this. So we will get T square divided by Tc square is equal to 1 minus Hc divided by Hc0. Now Tc square we need, so it will be T square divided by 1 minus Hc divided by Hc0. So what will get the answer? From there you have to get Tc value, though it will be root of all these 10, then it will come 8.58 divided by root of 0.5. Okay, then you will get the Tc value 12.133 Kelvin. So this is also basic problem. So if we just see the problems whatever we did today, so there are four different kind of problems. One is this basic formula HCT is equal to H0 times 1 minus T divided by TC whole square, and these are the one basic method is there. And then whatever we just calculate the critical temperature also like this, then critical current density. So these two formula you have to remember what is the critical current formula from using HC values and critical current density also. From that we went um, to use the formula for isotropic masses. So Tc, critical temperature, will proportional to the mass power minus 1 by 2. Using this we solved few problems today. So that is the fourth formula we were using today. Similarly here also Tc m1 proportion to the alpha, this alpha is isotropic constant. Total 5 formula we used today, and using this 5 formula we solve different kind of problem, finding critical current density and critical field, normal temperature and alpha value. All these kind of problems there will be present in the section. Okay, there are some more problems also, but now the time is not that, so we will solve the remaining problems. Actually there are 1 2 3 4 5 more 5 problems also there related to this same area, some isotropic masses related and critical field and critical magnetic field and current density and Josephson junction problem also there. So these 4 problems we will solve it in the next class. I hope all you understood the problems. Can anyone please respond? Okay, fine.
Yes, these problems which have we solved, I could understand.
Which problem?
All the problems, these are basic problems. That is okay.
Yeah, then. Okay, these are related to first week class. These are very basic problems, right? Start taught already the basics of superconductivity. So now next 4 week, next 3 more week, we will solve accordingly the week 2 problems related to week 2 theory. Whatever start taught, we will solve problems or whatever the kind of derivation or will be in the week 2. Similarly, it's corresponding we will solve here. Okay. Okay. See you then. We will meet the next class.
Okay.
Yeah. Thank you.
Thank you.